Keep an eye on the prize. All right. Hey, so guys, as we gather around this homework assignment, I want to lead you, first of all, if you would, to the questions at the end of the assignment. I think it started on number 15. And guys, looking at these questions down below, well, I guess I should do this. Does anybody need a copy of this first? Anyone else? You guys okay? Oh, all right. So, guys, we're not going to look in great detail at the questions down around 15 yet. But what I do want to do is remind you, guys, that questions 15 through 20, many of these were reflective. They were asking you to look for patterns. They were asking you to look at summaries. Guys, importantly, question number 16, we didn't even talk about. I was going over this last night with Jessica, and she's like, how are we supposed to know that when you didn't teach it? It's a valid question. We'll talk. But guys, understand, this is not a homework assignment that you have the luxury of just skipping off the top of and being okay. We're going to do a deep dive on this, especially questions 16 and 19, because those are going to become very, very important to us as we move forward. So with all of that said, let's start on number 1 and let's dig into this slowly. So guys, I'd really like all of you to join me at number 1, and we're going to think through this together. So, guys, the one thing that you learn to do in this assignment is identify the polarity of molecules. And guys, this is a process, but here's the problem. I didn't represent the entire process. Guys, what is missing from my answers that should be in yours? Your answers should look different than mine. And it doesn't have anything to do with this. Guys, what is in your answers that isn't in mine? Please. The polarities of the bonds. So now you're going, wait, why didn't you put in the polarities for the bonds? And guys, honestly, the answer was it created so much clutter that I just chose to delete them just for the sake of clarity. But guys, we need to talk about the way this works. This is an important concept, so join me in this. So what you're going to do is you're going to compare the electronegativities of all of the elements that are bonded together. So for example, carbon and chlorine, you may as well just turn your periodic tables over on the back and let's take a look. Guys, I believe carbon's electronegativity is 2.55. Is that right? Look at me go. Then guys, I believe chlorine's is 3.16. Is that true too? All right. So guys, what that means is chlorine is stronger than carbon. What that means is that this bond is literally drifting in that direction. You could even picture this pair of electrons being sucked over towards the chlorine. But guys, we've got another carbon-chlorine bond, and it's this one, and it's headed in that direction. So now we've identified the pole or the directions of those two bonds. So now we got to do carbon and oxygen. Again, carbon is 255. Is oxygen 44 something? What is it? I don't even know. 344. Okay, so oxygen's stronger, right? So oxygen is stronger than carbon, so that electron, those electrons are going in that direction. You okay? Are you sure? Okay. So guys, now we've identified the polarities of the bonds, and you should have this in your homework. Then we've got to figure out the overall polarity, and this is where this gets tricky, because that carbon is literally being stretched in all directions. But guys, which direction is it being stretched the most? Towards the chlorine or towards the oxygen? Why the oxygen? Keep going. Than the chlorines. So guys, oxygen is stronger than chlorine, which means that oxygen is the strongest dude in the neighborhood, which means the overall polarity is towards the oxygen, and that's the polarity of the molecule itself. So guys, talk me through questions. Yeah?
So if it was just like even one arrow pointing the other way, that's like 5, it would still go that
Yeah, and so that's the misconception here, but I want to talk about it because there's value. I've had people say, wait a minute, don't two chlorines beat an oxygen? And the reason that they don't is because all of these poles are symmetrical. Because these are all 120 degree angles, it turns out that if you think of, this is the way I think about it. If we were to pull this way, and this way, but that pole is the strongest, what direction does the carbon move? And the answer becomes the polarity of the molecule. So, guys, I didn't make it down to Spirit Bowl last year, but did we do the big group tug of war this year in Spirit Bowl? It's a good, I don't know, did we really have the three-way rope? Did we do that? Was it two? Okay, it used to be that we would rent actually a four-way rope. And so it was all tied together in the middle, and we'd have sophomores, juniors, seniors, and faculty all pulling at equal angles. But of course, the faculty always won because we have Coach Steele. But the idea is that we had four poles that were all maybe opposing each other, but because they were all at equal angles, the group that pulled the hardest was able to overcome all the rest of the groups, even though we weren't really stronger than everybody else. Because of the angles, this pole won. The same thing's going on there. Does that make sense, you guys? Is that okay? All right. So, guys, with that said, your question maybe is then, why did you do these? And guys, the answer is you didn't need to. I left them there because I've had people say, wait, how did you know the shape? Why did you draw this with 120 degree angles? So I gave you the names and angles so that you had something to sort of base your pictures on, but you didn't need to put the names and angles. All right. So guys, at that point, what questions do you have about identifying polarities, figuring out the bond polarities, the molecular polarities, all of that good stuff? Anything on 1 through 4? You okay? Please ask if you're not, guys. We're gonna dwell on this. We're in no hurry. You're okay? Okay. So, guys, moving along then. There we go. So, guys, talk to me about number 5. Why is number 5 not polar? What's the one-word answer? It's symmetrical. Guys, symmetrical molecules are not polar. We're going to talk about that in question number 19 in just a minute. But guys, please cement that in your brains right now. Symmetrical molecules are not polar. And so number 5 is symmetrical, so it's not polar. Guys, notice number 6 is polar. Nitrogen is not hydrogen. Therefore, if you were to draw a line of symmetry right here, it's not symmetrical because nitrogen isn't hydrogen, and that makes that molecule polar towards the nitrogen. Then guys, also down here, that dude is polar, again, because it's not symmetrical. You guys good? Yeah, Abby?
Actually, question number 2.
Mm-hmm. Yeah, hold on, let me go backwards. Go.
So, hydrogen, so you put the hydrogen on the left and then...
Mm-hmm. Yeah. Yeah, fluorine. Yeah.
Right?
Yep.
But I put fluorine on the left.
Okay. Did your arrow flip?
That way, yeah.
That's the trick, right? Which makes these really exciting to grade on the test because, yeah, you could flip the fluorine and the hydrogen, which is perfectly legitimate, but then your arrow has to flip. And so your drawings would be mirror images of mine, but the arrow should point at the fluorine because it's the strongest.
Okay.
Is that okay?
Uh-huh.
Okay. Guys, so I believe we're done with these. Are we done here? Okay, so let's go here. Again, guys, number 8, symmetrical, nonpolar. Number 9, symmetrical, nonpolar. Number 10, and guys, I don't know what happened to that hydrogen. Somebody cut its leg off. It doesn't look like that on my screen when I'm not in presentation mode. But the idea here on number 10 is that the chlorines are not hydrogens. So as a result, that means this molecule is polar towards the chlorine. But I've had people say this. What if I draw it like this? Because if I draw it like that, I don't know where... That's a hydrogen. If I draw it like that, then I don't know how to draw in the arrows. And so guys, when you're drawing these molecules, what you want to do is, if they have the possibility to not be symmetrical, draw them not symmetrical. So you could do it like this, and you could be like chlorines and hydrogens, but then the arrow would be coming out of the board, and that's really hard to draw. So what you want to do is you want to reorient it so you can draw the arrow in the plane of the board. Is that okay? So guys, are we good through 10? Good there? Okay. Then boom, and boom, and boom, and this is the rest of them. Our good friend water, remember that's bent, so we're going to draw it bent. Number 12 is symmetrical and therefore nonpolar. Number 13, that bromine breaks the symmetry, so it's polar towards the bromine. And then guys, OH, oxygen stronger than hydrogen, and off you go. You guys okay? Please.
So for molecules that have a 120 degree angle,
So trigonal planar?
90 degrees, is that okay?
Yeah, maybe. Here's my problem with that. So, for example, number 8, right? Well, better example. Let's go to number 1. If you had drawn this with 90-degree angles, I think you're going to end up in the same spot. And I don't know if this is exactly what you had in mind, but humor me. So you're like, okay, polar this way, polar that way, polar this way. But the misconception there is that these poles cancel out, and they actually don't. So in this class, you would be okay because you're okay. You get to the same place. But if you pursue this further, they'll actually have you looking at overall polarities in a way that's better than the way we do, and that would run you into trouble. So I would say, if you think of it, when you've got something that's trigonal planar, draw it that way. So, yeah.
I realized actually, I was talking about a shape of number 4. I drew number 1 at the angles. I don't know why I didn't do number 4. Awesome.
Well, so that would really perhaps be a mess, because if you took number 4 and if you drew it like this, you might think it's symmetrical. Know what I'm saying?
I drew it at 90.
So you went like, you went something like this?
Yeah.
So then did your polarity arrow go like that? Yeah, I mean, you'd be fine. That's fine. I mean, your angles are off by 30 degrees, but it's not life-threatening. So where did you put your unbonded electrons? Did you put them on the corner?
I just put them on top of it.
Okay. Yeah, so you got to the same place. You're okay. Yeah, great questions. Guys, anything else? Are we sort of connecting with these ideas? Okay. So, guys, what we're going to do today then is we're going to set the stage for extending beyond this. And in order to do that, I'd like to go over these questions with you. Now, guys, remember when we grade the homework, you're answering 2 questions, right? Is it done? And do you now understand? So, guys, when we get to question number 16, I fully expect you right now to go, we don't get it. You can still say yes if you get it after we talk about it. So guys, let's go through these. So question number 15 is a 3-part question about dipoles. Question number 1 is, what is a dipole? And guys, when you're doing this, carbon and nitrogen is stronger, and you're drawing that arrow, you're representing dipoles. So dipoles are the partial charge on a bond caused by unequal sharing. So how do we know which end is positive and negative? The easier way to answer that is, why is nitrogen the negative end of the dipole? Say it again. Not fully gaining, because that would be an ion. If these were, but why nitrogen and not carbon? You said it earlier. That's why I was glad you came back to it again. What do we know about nitrogen compared to carbon? Not bigger. It's actually smaller. There you go. It's smaller and stronger. So guys, the idea is the negative end of the dipole will be the more electronegative element. The positive end of the dipole will be the less electronegative element. And it's all about electronegativities. Is that okay? Okay. Then guys, question 16. I hope you didn't like this question. So now you're saying to yourself, then why did you ask the question? And guys, the answer is because I wanted to give you the opportunity to see if you could muddle through the answer. If you didn't get there, let's talk about it. So guys, question number 16 says this. Take these 6 atom pairings and put their polarities in order of decreasing polarity. So guys, this is the reasoning behind the question. So we've got chlorine, and we've got silicon, and then we've got chlorine, and then we've got carbon. Guys, find them on your periodic table. Chlorine, silicon, and carbon. Let's do the first pair first. And guys, please, if you're sort of zoning out right now, don't. What we're about to do is critical to your success today. So do this with me. Chlorine and silicon, which one's more electronegative? Chlorine. So what direction is this bond polar? To the right. So this bond is, no, it's not. It's polar towards the chlorine, right? Now guys, what about chlorine and carbon? Which one's stronger? The chlorine. So this bond is also polar towards the chlorine. Now the important question. We've never talked about this. Guys, which one's more polar? This is a brand new idea to you. Up until now, polarity for you was yes or no. Now polarity becomes a range of polarities. So which one is more polar? So guys, imagine this. Imagine if I took this rag, and I'm not going to ask you to grab it, but imagine if I had Harrison grab this rag, and he and I both pulled on the rag. And then imagine if I let go of the rag, and then I came over here, and I had Joe pull on the rag. Guys, what you're going to find is that this rag is going to be closer to me when I'm pulling against Joe than when I'm pulling against Harrison. Why? Harrison's stronger than Joe. The assumption is that I'm stronger than both of them, which probably isn't true. But the idea is that Harrison is stronger than Joe. So if I pull against Harrison, he's about my size. I'm a little stronger maybe. So this is going to be a little bit closer to me. But if I pull against Joe, it's going to be even closer to me because I'm more stronger than Joe than I am Harrison. Was that a sentence? Do you know what I'm saying? I'm more stronger than her than I am him. Apply it to this. Do you see the connection? Guys, I'm the chlorine, and I'm stronger than Harrison, and I'm stronger than Joe. But now we got to figure out which one I'm more stronger than. So let's get some numbers. Help me. What's the electronegativity of chlorine? 3.16. 3.16. What's silicon? 1.90? Yeah? Thank goodness. That makes the math easier. What was carbon? 2.55. So guys, this is a new skill that you need today. We can calculate the polarities of these bonds. We do it by subtracting. So if you take 3.16 and subtract 1.9, is that 1.26? Is that right? So guys, that bond has a polarity of 1.26. Now when we come down here to do this one, what's 0.45 and 0.16? 16. So guys, this bond has a polarity of 0.61. That means that this bond is more polar than this bond because these are both chlorines, but silicon is weaker than carbon. Do you see how that works? So guys, fundamentally, here's the skill. If you want to find the polarity of a bond, subtract the electronegativities, and that is where these numbers come from. And those numbers are representative of the bond polarities, but apparently I made a little error because I had 0.60 instead of 0.61, but I think it's still correct in order. Please.
Sorry, I think I was with him. I think that it is out of order. I had two answers, specifically like E and C, where those ones don't match up.
Oh, really?
Oh, yeah,
For-
C is way off.
Yeah, it's 1.66 and 2.
Okay, here, there's the nice thing about being in a collaborative relationship with another teacher is I can just blame Miss Call. So let's just blame it on her, and then we're good. So which one are you saying's messed up?
So it's C that was the most messed up. It's CMO and T.
This is the one that you did the worst. Okay, so 1.66 is molybdenum, and beryllium is... Where's beryllium?
It's further down that line. It's
On like the middle one.
Oh,
52.
so that's a difference of 0.44.
Yeah.
Oh, shoot. So this should be 0.44. Is that right?
Yeah.
Okay. Keep going. Here, you know what? While you're correcting these with me, or let me write this down. So you're saying that this is 0.44. What else did I screw up? Guys, did any of the rest of you catch these mistakes? Sorry. What else?
I don't know why, but like I looked at the same answers when I looked at the electromagnetic
Yeah.
online, and then it had like ones that made it like match that.
Oh, well, and that's really interesting, guys. What you're going to find is that, and I'm sure you never even noticed this, but if you do, don't. But if you do look in your periodic table at the key in the bottom left-hand corner, it says electronegativity, but it also says Pauling's electronegativity. There are multiple electronegativity scales. I wonder if I based it on a different scale. It's possible. So, guys, let's do this. Rather than swatting at gnats and choking on camels, are you guys familiar with that idea? Rather than swatting at little things and missing big things, let's just say this. Guys, did this idea make sense? That's the big idea. I'm sorry if I got the numbers mixed up. I'll fix it. But guys, if you understand this idea of figuring out the polarity of a bond by subtracting, your money. At that point, the rest is details. You guys okay? Can I get an amen? Amen. All right. Are we really okay? I don't want to cause confusion, but I don't want to dwell on subtraction errors. You're okay? All right. So, guys, then looking down at number 17, it might be worth looking at these carefully. Grab your homework paper, and, well, here, I'll put them on the screen. So, guys, the first one is The first one is HBr. And here's the question. Without drawing this thing, is it polar? And guys, the answer is yes. Why? Because hydrogen's not bromine. It's not symmetrical. If you've got two atoms and they're not the same, it can't be symmetrical, so it's got to be polar. Then, guys, this, CF4. A little more of a stretch, but I'm going to tell you right now it's not polar. Why? Because it's symmetrical. But then we got to ask the question, why again? Guys, if you've got four things bonded around a central atom, what's its structure going to be? Tetrahedral. And if you've got something that's tetrahedral and all four things are the same, it's going to be symmetrical and not polar. Okay. Then, guys, the last one was Cl2. This is not polar. Why not? Same thing, it's symmetrical. It's like this, only they're the same things, right? Here we've got an H bonded to a Br. Here we've got two Cls bonded to each other. That makes it symmetrical and not polar. Good? By the way, guys, you ready for an interesting thought? This is why Cl is red on the periodic table. What does red mean? Gas. Guys, chlorine, when you find it in nature, is actually a chlorine bonded to another chlorine. That thing is symmetrical, therefore it's not magnetic, therefore it's not sticky, therefore it's a gas. So guys, that's why chlorine is a gas, and that's where we're headed with this today. Are we good on 17? Okay, let's finish this up, but let's not hurry because 19 is important. So guys, number 18 is all about this idea about symmetry being tied to polarity. But then guys, number 19. Here's the deal on number 19. What number 19 is doing is it's asking you to find the patterns. It's asking you to figure out why molecules either are or are not polar. Now, guys, we understand it's about symmetry, right? Symmetrical molecules, are they polar? Symmetrical molecules. not polar. Non-symmetrical molecules, polar. And guys, that's the way we're going to approach this question. If we can figure out what makes molecules not symmetrical, we can then figure out what makes them polar. So guys, let's look. Do this with me. Start on number 1. Let's figure out the patterns. What makes molecules not symmetrical and therefore polar? So guys, number 1, not symmetrical, therefore polar. Number 2, not symmetrical, therefore polar. Number 4, not symmetrical and therefore polar. Number 3, symmetrical and therefore not polar. Guys, we don't need to look any further. If we can figure out why 1 and 2 are symmetrical, we're halfway there. If we can figure out why 4 is symmetrical, If we can figure out why 1 and 2 are not symmetrical and therefore polar, we're halfway there. If we can figure out why 4 is not symmetrical, we have all the pieces of the puzzle. So guys, why are numbers 1 and 2 not symmetrical and therefore polar? Yeah? Yeah, well, different atoms, sure. However you want to say it. Guys, chlorine, chlorine, oxygen. These atoms are different. As a result, this cannot be symmetrical. If you have different outlying atoms, those molecules can't be symmetrical, so they've got to be polar. Same thing here. Hydrogen is not fluorine. Different atoms, not symmetrical, polar. But guys, look at number 4. Those are the same outlying atoms. This is oxygen and this is oxygen. So those are the same atoms. So that violates the first rule. But why is number 4 not symmetrical? Yeah, Jess? It's all about the dots. Guys, that's it. Every single molecule that has dots on the central atom, or every single molecule that has different outlying atoms, will be non-symmetrical and therefore polar. So guys, let's test our hypothesis. You ready? Let's look at number 5. Does it have dots? No. And we're talking only dots on the central atom. Does it have dots? No. Are these atoms all the same? Yes. Not polar. What about here? Are there dots on the central atom? No. But, oh shoot. There are no dots on the central atom, but guys, you'll notice that hydrogen is not nitrogen. That's polar. What about down here? These atoms are all the same. Why is it polar? It's got dots. Do you see how that works? So guys, it's really that simple. Go down to your answer to question number 19. And if you don't have this, I would strongly encourage you to not only write it down, but star it, underline it, tattoo it on your arm, whatever you need to do. Guys, this is it. If you can keep track of this, your life's going to be a whole lot easier. If it's got dots, it's only on the central atom. If it's got unbonded pairs, I should include that on the central atom. That's important. Or if the outer atoms aren't identical, that thing's going to be non-symmetrical and therefore polar. And then guys, wrapping up, question number 20 says, how is it that molecules with polar bonds can be non-polar? And it's all about symmetry. The bonds cancel each other out, and there are some examples there. So, guys, questions about any of this? You okay? Did you ever think we'd spend 30 minutes grading homework? You really okay? All right. So, guys, let's do this. Let's get this recorded. And today's short. Sir. Correct. Yep, that's it. So, very well said. So, to find the polarity of two atoms involved in a bond, subtract their electronegativities. Yep, you got it. All right, so let me put this away. Joe, just to clarify, I didn't call you weak, right?
No, I'm offended.
You know what we should do is we should have you and Harrison tug of war just to verify the concept.
I mean, you hurt my feelings
Oh, shoot.
All the crap talk that we were doing. I got to
That's
tell you I wouldn't.
that's funny and yet very sad. All right. So Kanani's gone. Ami, you good on this now? Yeah. Michael, how about you? Ellie, you good? Kale?
Yeah.
Josh? Kyson, you good on the homework? No. Bree, how about you? Bethany? Hey, did we establish it when you're going to take the test? Say it again. You bet. Absolutely. Okay, sounds good. Harrison, you good? No. Mila? Alex? Beautiful. David, you good? Not a kid. Joe? Sabrina? Kimberly, you good? Yes. And Rachel's gone. Jesse? Jasmine, you good? Matthew, how about you? Abby?
Yes.
Joe?
Yes.
-1. Ha! I don't even know what that would do to your grade. Esme?
Yeah.
Sophia?
Yeah.
Caleb's gone. Anaya's gone. Kira?
Yeah.
Caden, you good?
Yep.
All right. So, guys, grab something you can take notes with, something you can take notes on. Periodic tables flipped over to electronegativities. Here we go. All right, gang. What do you want?
So I've actually found that two atoms have the same.
Sure, right?
Would they actually?
Yeah, so would it be nonpolar? It's a really interesting question, and the answer is no. It would still be polar. The reason is because these electronegativities are approximations. They're only 2 significant digits. This is the part of the answer you're really not going to like. So we talked about the idea that chlorine bonded to chlorine is nonpolar, right? Guys, you can completely disregard in a minute everything I'm about to say. This is AP stuff. So we talked about the idea that chlorine bonded to chlorine is nonpolar because these are the same atoms, right? And that's true, except for, let me give you a better example. And that's true. Let me use this as the better example. So guys, David's question was, if we have 2 atoms that have the same polarity, are they nonpolar? Here's a better example. This is nitrogen. Triple bonded together, same atom, strongest bond in nature, interestingly. Nitrogen triple bonded to nitrogen is the strongest single bond in nature. Wildly symmetrical and therefore not polar. Here's the problem. Again, I'm going to have you catch. We can liquefy it. And if we could, because 70% of the air that we breathe is nitrogen. So how can we liquefy nitrogen if it's nonpolar and therefore never sticky? I'm sorry, yeah, nonpolar, symmetrical nonpolar, therefore never sticky and should never be able to liquefy. And the answer is even something like this is slightly polar. So the question is why? And the answer is, what do these sticks represent? Well, the sticks represent the electron clouds, right? And we understand that these electron clouds are probabilities. And over time, they look symmetrical. But at any given moment, there's the possibility that these electron clouds could be slightly lopsided because they're probabilities. And because that's the case, there's no such thing as perfect symmetry, which means that any molecule could be momentarily lopsided and therefore polar. And that's enough to be able to even get this to stick together and liquefy. Yeah, they're called instantaneous dipoles, and we talk about them. We talk about them in AP, but we're not going to do that in here. So, but great question. Are you guys ready to move forward? Okay, so guys, this is why we had all the time that we needed to do what we just did. What we're going to do today is actually the first of a 2-day process. So guys, if you look at your homework with me really quick. Look at your homework. Do you have your homework packets out still? Look at the next assignment with me. If you look at the very tippy top, do you notice what it says? 2 and 3. So guys, what we're going to do is we're going to start this assignment and this conversation today, but we're not going to bring it full circle until Thursday. So guys, join me on the journey, would you? Join me up here. So let's talk. Here's where we are right now. We did a deep dive on polarity. We understand that bonds are polar because the atoms have different strengths. We understand that the molecules are polar if they meet what two criteria? Let me say it again. So guys, we understand that bonds are polar if they aren't the same atom. But we understand that molecules are polar if they have one of two things. What are those two things? Question 19. Dots on the middle atom or not the same things around the outside. You good on that? So that's where we are right now. Here's where we're going today. Guys, we're going to ask the so what question. So what? Who cares if they're polar? And what you're going to find out is that polarity gives them something called intermolecular forces. Think about magnets sticking together and you understand the concept. But guys, that's where we're going to stop today. We're going to be done in about 20 minutes. Then, guys, we're going to take the next step on Thursday, and we're going to ask another so what question. Okay, so what? They're sticky. So what? They have intermolecular forces. And, guys, on Thursday, we're going to talk about how that changes the way things behave. We've already touched on it. Like nitrogen tends to be a gas because it's not polar, so it's not sticky. That's where we're headed. But we're only going to get to intermolecular forces today. So, guys, this is the way we're going to roll this out. If we're going to talk about intermolecular forces, we got to define it first. So I'm going to define it for you. Then we're going to come back and we're going to draw 3 more molecules and we're going to connect polarity to intermolecular forces and then we're done. Short time. You guys ready? Okay. So first of all, let's define what intermolecular forces are. So actually here, I'm going to jump around in the slides a little bit. We've already done a lot of this already. Yeah, we're going to start right here. Okay, so guys, this is where we're going to start, and I would strongly encourage you to write this down. Intermolecular forces, bless you. Wait, did you find that offensive, or are you going to report that?
Oh, yeah.
Because that was like
I'm
church.
actually recording.
Shoot. In my AP classes, a lot of times the kids actually do record class, and then last year they made a mashup of all the stupid stuff I said in class over the year, and they gave it to me. Yeah, it was wildly embarrassing. I'm pretty sure they violated my civil rights, but I'm not really sure. Realizing that teachers have no rights, and so at that point it doesn't matter. Okay, so guys, what are intermolecular forces? And it goes like this, and probably as you're reading over this, you're going, oh, yeah, that feels okay because we already talked about it. So guys, this is the idea. Polar molecules. Can you picture all those molecules that you drew that were polar? Polar molecules. When they get together in groups, they're attracted to each other. Why are they attracted? Well, guys, they're kind of like magnetic. Don't take that too far, but it's really the case. We've got a positive dipole, we've got a negative dipole, and we know that positives attract negatives. And so, guys, literally what's going on is positive dipoles are attracted to negative dipoles, and negative dipoles are attracted to positive dipoles, and we got all these attractions going on, and all of these attractions make these dudes stick together. Those forces of sticking together we call intermolecular forces, or IMFs. Now, guys, understand inter means between. So these are forces of attraction between molecules. We're just getting started and we're almost done. You guys okay? So guys, there's a couple things you need to know about intermolecular forces. Just things that you need to keep track of along the way as we get into these. So, like Joe, they're weak. I just can't resist poking the bear. If she's going to take me down, she's going down with me. No, but in all seriousness, guys, these intermolecular forces are weak. And surprisingly, the analogy, actually, the little wrestling thing we did, even does come into play here. Guys, when we say weak, do you understand that weak is a comparative term? Because Joe is weak compared to Harrison, probably, or me. But there's lots of people she's stronger than. And so, guys, when we talk about this idea of weak, understand that it's comparative. So, guys, when we say weak, weaker than what? Any thoughts? Weaker than what? Weaker than those forces. But, guys, even more importantly, weaker than the forces that hold the molecules together. And what are those forces? They're bonds, covalent bonds. And so, guys, when we say weak, we mean weaker than covalent bonds. It's about 1/10 to 100th the strength. But, guys, please, weak does not mean unimportant. So much of the world that we live in functions the way that it does because of these weak intermolecular forces. Guys, this unit is fascinating as it rolls out because these intermolecular forces are all around us and they do amazing things. So, this then, guys, becomes where we're going to wrap up our day. When we say weak, we mean weaker than covalent bonds. But, guys, you'll notice there's a range, 1/10 to 100th the strength of a covalent bond. So which one is it? Is it 1/10 or is it 100th? And guys, the answer is it depends. What does it depend on? Polarity. Because not all bonds have the same polarity. That was the point of question 16 that I botched up, that you guys were giving me better numbers for. Because that's the big connection here. This is where we're headed with this. We are going to figure out the polarities of the bonds. How do we do that? Kyson, you did a great job of reviewing for us. How do we figure out the polarities of bonds? We subtract their electronegativities. Once we know the polarities of the bonds, we can figure out the polarities of the molecules. If we know the polarities of the molecules, we can figure out the strengths of their IMFs. Do you see how all those pieces fit together? Can we do that one more time? So, guys, the idea is this. If we can figure out the polarities of the bonds, and Kyson said, how do we do that? We subtract. If we know the polarities of the bonds, we can figure out the polarity of the molecule. If we know the polarity of the molecule, we can figure out the strengths of the IMFs. And that's where we're going to stop today. Does that sit okay? So, guys, how then does this relate to IMFs? The more polar the molecule, the stronger the IMF. If a molecule is more lopsided, it'll be stickier. Good? Okay. So, guys, may I move forward because this is all going to go away? You're all right? Okay. So, guys, one last thing. Don't write this down. Please don't write this down, but I need to tee this ball up for you right now. Guys, throughout the rest of the year, let's even do it here. Did you notice what I just did? Following me again. So we're going to figure out the polarities of the bonds. This gives us the polarity of the molecule. This gives us the strengths of the IMFs. Guys, these are cause and effect relationships. Bond polarity causes molecular polarity causes IMFs. Guys, these are all about cause and effect relationships. And if you want to think about cause and effect relationships, you've got to learn to use the word, don't write this down, you've got to learn to use the word therefore. So, high polarity, bond polarity, therefore high molecular polarity, therefore strong IMFs. But guys, are you familiar with this? Do you know what that is? This triple dotted triangle? Guys, this is the mathematical symbol for therefore. And you're going to use it a lot for the rest of the year. So if you didn't know, that is the mathematical symbol for therefore. So you'll see how we use it in a minute. You guys okay? Okay. So guys, do this. Please, in your notes, you're going to need about 1/3 of a sheet of paper. So if you're running low, you shouldn't, but if you're running low, flip to the back. Guys, across your paper, please, write these down. CH4, CH3OH, and H2O. We're going to draw the Lewis dot structures for these molecules. But guys, we are going to do this very carefully and very well. You've drawn these already, so I'm going to step you through it. But guys, remember, all of this depends upon symmetry. So we are going to draw these as three-dimensionally accurately as possible. Guys, pause for a minute, would you? Let's just start at CH4. Is that thing going to be symmetrical? Yeah, same example as that one we looked at in class. It looks like this. Would you draw it, but would you draw it big? Maybe about 1.5 inches across. Spread these out. Give yourself space. So guys, if you're ever looking for a masterful class on how to use the word therefore, the book of Romans. Paul is a genius. I don't know if you've ever read through the entire book carefully, but so many of the chapters in the book of Romans begins with the word therefore. He's making an argument. I prove this, now I'm going to convince you of this. He's a master of that. It's good stuff. I remember somebody taught me that anytime you see the word therefore, you should ask yourself what it's there for. Huh? See? Little seminary lesson. All right, you guys good on CH4? You good on that one? Okay, so guys, CH4 is tetrahedral. You don't need to draw that, but we're all making connections, right? Okay. Now let's go over and let's do our good friend water. Why are we drawing it like that? Because it's bent. The model looks like this, but you don't need to draw it. So guys, now you're asking yourself, wait, why did you go left and why did you go right? Why did you skip the middle? Do you see? Because it's special. Do you see the connection? And I actually mean the word connection. Do you see it? Yeah. Guys, check this out. You pull a hydrogen off of here, and you pull a hydrogen off of here, and you mush them together, and you get that. Over on the left is our CH3. Over on the right is our OH, and you put them together, and you get CH3OH. Huh? Oh, yeah. What's that? CH4 is methane, which is Bunsen burner gas. Water is water. So what's the thing in the middle? So methane, right? But the addition of this OH makes it a substance called an alcohol. So this is actually called methyl alcohol or methanol. It's wood alcohol. This is the stuff that caused people to go blind during Prohibition because they were making moonshine stills out of wood rather than metal, and the methanol was leaching out of the wood, and it actually causes blindness. So, yeah. Yeah. So methanol, the molecule in the middle, it does impair judgment. It gets you drunk like ethanol, but then it also makes you blind. A lot of people went blind during Prohibition because they were drinking methanol without knowing it. So guys, let me show you quickly, if I may. The molecule looks like this. I have built, or at least at one point I had built all of these. So let me put these back together, which apparently I can't do. And like this, and like this, and like this. And so guys, here we got CH4, we've got methanol, we've got water. It looks like this. You guys good? This is how we're going to wrap up the day. We are going to figure out the polarities of these molecules. Guys, this is your goal for today. We are going to put these in order by polarity. Least polar, middle polar, and most polar. So guys, let's do a gross observation first. Is this symmetrical? Yes. Is it polar? No. Okay, now what about this? Is this symmetrical? And you can clearly see it, but let's be sure we understand why. Guys, it's the same atoms over here. Which test does it fail? Dots on the central atom, right? So now what about this? Is this symmetrical? No, why not? Dots on the central atom. We're going to call oxygen the central atom. It's got dots, so it's not polar. So now, guys, we're going to put them in order by polarity. So which is the least polar? Left, middle, or right? Left, because you can't be less polar than not polar. So, guys, that is the least polar, number one. Now we've got to figure out which one is more polar between the methanol and the water? Now, how do we know? And actually, you're wrong. How do we know? Sorry. No, wait, hold on. Maybe I'm wrong. Did I say least polar?
You said most.
Oh.
I am wrong.
Actually, you are. So, guys, here's the big idea, though. How do we know? How do we know? How do we compare polarities? We've never done this before. And the answer is this, Kyson, and this is why I was so glad for your question. Guys, we got to figure out the polarities of all of these bonds. But to figure out the polarities of all of these bonds, what do we subtract? The electronegativities. Wouldn't it be nice if we knew the electronegativities? Almost like I knew this was coming. So, guys, what we've got to do now is we've got to do the math. I would strongly encourage you to not write the numbers down, but I would strongly encourage you to write down the numbers that I am going to write down. So, guys, let's start with the clearer picture over here on the right, and let's figure out these polarities. So let's draw arrows first. Does the polarity arrow point towards the oxygen or the hydrogen? The oxygen. So would you draw that in with me? This is important. And then, guys, what about the other bond? Obviously towards the oxygen, like so. Guys, forgive me for grabbing a finer pen. I know it doesn't stand out as well, but we're going to need to keep down the clutter. So that's old stuff, right? That's what we did last time. So now let's do this. Let's quantify the polarities of those bonds. And again, to do that, we subtract. And I believe the difference is 1.24. Is that true? Okay. So guys, let's write that in. This has a polarity of 1.24. This has a polarity of 1.24. Is that okay? Now, guys, let's do this. Let's draw in the polarity for the overall molecule. Can you picture it in your mind's eye? Where does it go? Bottom left? It's kind of like disco. So it goes bottom left to top right. Okay? So, guys, this overall arrow goes like so. Can we draw that in too? Okay, so let's stop there for a moment. And now let's group around methanol. And let's draw our arrows first. Guys, let's start on the left. Carbon is more electronegative than hydrogen. So all three of those bonds go to the carbon. Is that okay? So we're going to go 1, 2, and 3. Now, guys, what about carbon-oxygen? Towards the oxygen. And then what about oxygen-hydrogen? Towards the oxygen, like so. Okay. Now, guys, I'm going to reverse the order that we're going to talk about the next two ideas. On water, we did the subtraction and then we did the arrow. We're going to save ourselves some time. Let's do the overall arrow first. So, guys, picture this and let's think. So these are all closing in on the carbon. Hydrogen is closing in on the oxygen. But all of this is flowing towards the oxygen. So what is the overall flow? Can you picture it? So this is flowing this way, and this is flowing this way, and overall the flow, can you see that the overall flow is like this through the oxygen? Is that okay? Again, guys, if you've done physics, these are vector sums, but if you can just picture it in your mind eye, that's fine. Okay. So now, guys, now that we've done this important work, we need to now figure out the polarities of the bonds. But here's why we drew the overall arrow first. This makes our lives easier. I'm going to make a mess and then clean it up. Guys, the only bonds that we've got to figure out the polarity for are the bonds that are directly neighboring the overall polarity arrow. We don't have to do these subtractions because they're not as important. So all we've got to do is look at these two bonds. Did you catch that? That's important. Guys, only do the subtractions for the bonds that neighbor the overall arrow. So we've already done this one. This is 1.24. But then, guys, we've got to do the oxygen-carbon, and it's early. I don't trust myself to do math, especially given how bad I screwed up that homework assignment. So I've got 3.44 minus 2.55, 0.89. Can you confirm that? Okay. Now, guys, this. Here's the big idea. The more polar the bonds, the more polar the molecule. So let's look. Here we have a polarity of 1.24. Here we have a polarity of 1.24. Here we have a polarity of 1.24. Here we have a polarity of 0.89. So which one is going to be more polar, the water or the methanol? Why the water? Because its bonds are more polar. These are a tie, but this is more polar than that. So guys, water has a greater overall polarity in the neighboring bonds. So this dude over here will be, if it comes up, the most polar. And then guys, methanol in the middle will have a mid-polarity. So Michael, I know I kind of called you out, but does that make sense?
Yeah, that makes sense.
Okay. So guys, that's it. We're done. That's the big idea for today. Hopefully now you see why the homework that you did was leading towards this and why we spent so much time dwelling on making sure we were good on the homework. But guys, this is the big idea for the day. So let's sort of summarize a little bit. So we understand now that polarity, that symmetry is important. Symmetrical molecules are not polar. If you've got molecules that are not symmetrical, they are polar. The things that make them not symmetrical are dots on the central atom or different outlying atoms. Then, guys, we extended that a little bit, and we talked about this idea of intermolecular forces, stickiness. So what makes a molecule sticky? And the answer is polarity. But now we understand that not all polar molecules have the same polarity. And this is the process of figuring out what they are. And now we know, guys, this final thought, and then we're going to wrap up. Guys, which one of these molecules will have the weakest intermolecular forces? I know that this is foreign, and we haven't this is what we're doing Thursday, but I'm setting the table. The more polar the molecule, the stickier, the stronger the IMFs. So guys, which one will have the weakest IMFs? CH4, because it's not polar. So what? We'll talk on Thursday. Guys, which one has the strongest intermolecular forces? Water. So what? Well, guys, this is the so what. Guys, these molecules are polar. And because they're polar, they're literally sticky. They stick together, negative dipole, the positive dipole, they literally stick together. But when you get a bunch of them together, they all stick together, and that's why water's a liquid. That's where we're headed with this. Do you see the big picture? Okay, so what are we doing for homework? Guys, be really careful about this because you might get frustrated. Grab your homework and let's talk. So guys, on the homework assignment, what do the triple dots mean? Therefore. So guys, first of all, this. You don't need to write this down, but you're only doing the left and center columns, not the right. That's going to be Thursday's homework. Only left and center. What that means, guys, is you cannot do number 1 because you have no information for number 1. But you can do number 2. And guys, this is what it's saying. Do this with me. If you have a molecule with a low polarity, the down arrow means low. Low polarity, will that have strong or weak intermolecular forces? Weak. Therefore, the IMFs are weak. Number 3, you can't do because you have no information. Now, guys, what about this? If you have molecules with strong intermolecular forces, number 4, if you have strong intermolecular forces, will you have high or low polarity? high polarity. Strong IMFs are therefore caused by high polarity. So guys, fundamentally, these relationships are direct. If one is big, the other's big. If one is small, the other's small. Are you done with this page already? I'll give you a second to finish it if you need. One is big, the other's small, the other's small. They vary directly. You good? Okay, then guys, do this with me. The next page. You're going to do this. Here's what it says. For each of these molecules, draw both the Lewis dot structure and the molecular polarity. Because that's what we just did on the board. Draw these Lewis dot structures and the polarities. Then this. Identify, let me read it to you. Then circle the more polar molecule. And guys, this idea about explaining your reasoning, cross that off. You don't need to do that. The reasoning is math, right? Just like we did in the notes a minute ago. But guys, notice that there are pairs of molecules. Do methyl chloride, CHCl3, and methyl bromide, CHBr3. So do both of them, figure out their polarities, and then circle the stronger one. Got the idea? Guys, with that said, this, number 5 and number 6, please don't try to draw those Lewis dot structures on your own. You could do methanol, because that's right out of our notes, right, on number 5. But guys, do not try to do diethyl ether on your own. It's tricky. I wouldn't expect, hey, just one second. I wouldn't expect you to know this. So guys, just copy it out of the notes, out of the homework answers. Then guys, on number 6, acetone, that's fingernail polish remover, and propanol, don't try to do those on your own. Also pull those out of the answers as well. So guys, you've got about 15 minutes left. Let's get a head start on this. Start drawing these things. I'll put the answers up on the wall. And then guys, we'll grade this on Thursday, and then we'll move forward on Thursday. Please. Yeah. You guys good? Okay, let me shut this off.